Okay, welcome to the end of Chapter 8. Chapter 8 is all about hypothesis testing, which is a very big, challenging subject. And so we spent almost a couple of hours introducing the idea in 8.1 with the basics of hypothesis testing. And we looked at the idea of having a claim about a parameter and using that claim to formally construct a null and alternative hypothesis for a hypothesis test, and having a significance level, an alpha value at which you're going to run the test, and then ultimately the most common approach being to then produce from a sample a p-value from a sample based on assuming the null hypothesis. And then if the p is below the alpha value, you reject the null hypothesis. If the p is low, the null must go. And that supports the alternative hypothesis. If the p is not low, you fail to reject the null, and there's insufficient evidence in support of the alternative hypothesis. So that was sort of the big idea. And now we're spending the rest of Chapter 8 trying to put that into practice and to understand it better, because practice makes your understanding better. And so in 8.2, we applied that concept to testing a claim about a proportion. And then in 8.3, we applied that claim to, applied that process to testing a claim about a population mean. And now we're going to finish up by testing a claim about a population's standard deviation or variance. Again, the variance is the square of the standard deviation. So that's our goal for today and the final topic of Chapter 8. So key concept. This section presents methods for conducting a formal hypothesis test of a claim made about a population standard deviation, sigma, or the population variance, sigma squared. The methods in this section use the chi-squared distribution. Chi-squared distribution. So the symbol for the chi-squared distribution is like a big X with a square. It's usually in italics as well. So let's remind ourselves of the overall structure. And I'll use symbolic notation here. So you're going to have some sort of a claim. And in this case, for this section, we're talking about a claim about the standard deviation of a parameter of a population. For example, the standard deviation of the heights of students at DVC. And so let's say our claim is that the standard deviation of heights of students at DVC is greater than 3 inches. So notationally, that would be something like sigma is greater than 3 inches. And from the claim alone, you can construct your null and alternative hypotheses. So from that, I would be able to say that I could make a null hypothesis. And the null hypothesis will always be equality for the specified value. So if the claim specifies sigma is greater than 3 inches, then the null hypothesis would be that sigma is equal to 3 inches. And then the alternative hypothesis. The alternative hypothesis will be a greater than, a less than, or a not equal to. And if your claim is greater than or less than, the alternative hypothesis would then be your claim. So in this case, my alternative hypothesis would be that sigma is greater than 3 inches. I would also need to set an alpha level. The most common is 5%. But it could be 1% or 10% or whatever. So then you would collect a sample and you would assume the null hypothesis And based on the assumption of the null hypothesis, based on assuming the null, assume the null, and then based on the assumption that the sigma value for the population is 3 inches, you would use sample results and create a chi-squared distribution. So then you would use sample results on chi-squared distribution. And based on the sample results on a chi-squared distribution with the null and alternative hypothesis that you've constructed, you would use technology to determine the p-value. And then if the p is low, the null must go. Meaning if the p-value is less than your alpha value, in this case 5%, then you would reject the null would go, you'd reject the null hypothesis and say that the sample provides evidence in support of the alternative hypothesis. Or if the p is not low, is not below 5%, then you fail to reject the null hypothesis because the sample does not provide sufficient evidence in support of the alternative claim. It does not give you sufficient evidence to reject the null hypothesis. And this is how we use a procedure to perform a hypothesis test for standard deviation. So it's the same concepts, the same setup, the same process that we talked about in 8.1. And now at the end of the chapter, we're applying it to standard deviation. Now, in all of the language in this key concept, they're talking about the standard deviation or the variance. And what you'll find is that a lot of the problems in my stat lab are talking about standard deviation. But actually the tools in StatCrunch are based on the variance, the square of the standard deviation. So as I showed in my example problem that I did on using StatCrunch on Canvas, and as we also saw when I was doing the same thing for the confidence intervals in the previous chapter, when you're using the StatCrunch tools, you often have to take standard deviation values from a problem in my stat lab and square them to get variance values when using StatCrunch. And then when you get results in StatCrunch, you have to square root to go back to get results about standard deviation. So we will see that in action, but just a reminder that there's this difference often between what the problem is talking about and what the tool wants to use in StatCrunch to do the number crunching. Are there any questions, comments, discussion about this sort of reminder of the hypothesis testing process and how it relates to our key concept for this section? Questions at all?
You had a quick question. You said if the P is low, then the null must go, and then you would support the alternative claim, right? And if the P is higher, then you would fail to reject the null, and then what? You wouldn't still support the alternative, right?
Correct. And you would usually say something like there's not sufficient evidence to support the alternative claim.
Okay. All right.
Does that make sense?
Yeah.
Moving on. All right, so they're going to now state our objective for this section is to conduct a hypothesis test of a claim made about a population standard deviation or population variance. And I just sort of described the idea of that process that we want to be able to conduct this test for. And so they remind us the basic notations involved: sample size, standard deviation, population standard deviation, either sample or population. And then if you square either of those, you get the variance for the sample or the population. Now, I want to sort of remind people that the chi-square distribution is not a normal distribution. It's a skewed normal distribution. And they're going to help illustrate that for us in a bit here. Testing claims about sigma or sigma squared requirements. So there are requirements in order for us to perform a hypothesis test when we are working on a particular problem. First of all, is that the sample is a simple random sample. Basically, as usual, bad data means bad results. And the way you get good data is by having a simple random sample. That's the golden idea. The population has a normal distribution. This is a fairly strict requirement. So in the previous section where we looked at doing a hypothesis test for a mean value of a population, well, then you had an alternative to the original population being a normal distribution for your parameter. You could also just have a large enough sample size to take care of that. So if your sample size was over 30, that was sufficient, and then you didn't have to worry about whether the population had a normal distribution. But because of the chi-square distribution being sort of lopsided, you have to use these methods only if you have a normal distribution from the population parameter. In this case, the samples, whatever it is you're sampling from the population has to be distributed normally. If I'm looking for the standard deviation of student heights, then student heights need to be normally distributed for me to use these methods for the hypothesis test. And so how would you know that? Well, most of the time, the problems are just going to say that. Most of the times, the problems are just going to say, assume this comes from a normally distributed population in order to fulfill this requirement. However, just to point out, this can be checked because we've done that before. We've checked whether we believe sample data came from a normally distributed population. And the way we did that was we used a histogram of the sample to see if the sample was normally distributed, as well as a normal quantile plot to see if the data seemed to fall reasonably close to a straight line without a systematic deviation from that line. And if that was the case, then we concluded that it appears that the data comes from a normally distributed population. So if we have data that we're collecting because we're wanting to do a hypothesis test about a standard deviation, then this fairly strict requirement that the population has a normal distribution can be checked by using a histogram and QQ plot, or normal quantile plot. So it is possible they'll give you a problem where they'll give you data and suggest that you try to do a hypothesis test in which somehow the correct answer for the problem is that we can't trust the results of the analysis because it looks like the data comes from a distribution from the population that's not normal because the QQ plot doesn't follow a straight line or something like that. So it's possible. Most of the problems don't do that at all. Most of them just tell you in the problem, assume it comes from a normal distribution. But just let you know, that's part of what our discussion will be about in this final section here. So having said that, these are the requirements. Then they give us a formula that we typically won't use. This is to get the test statistic. And again, we will be using technology to get the test statistic. And critical values can be done, but we're going to use a p-value ideally instead. So when testing claims about standard deviation or variance, the p-value method, the critical value method, and the confidence interval method are all equivalent in the sense that they will always lead to the same conclusion. And so ideally, the confidence interval method was introduced in Chapter 7. The critical value thing we saw somewhat in 8.1, but the p-value method is easiest, and it's the best place that helps you focus on the understanding by thinking about what the p-value is. I had a discussion about that in our 8.3 introduction, really focusing on the p-value for a few minutes. So take a look at that if you get a chance. All right, so any one of these methods should work and the p-value wins. So now they're going to remind us of the properties of the chi-squared distribution. So as I mentioned earlier, the distribution is not symmetric. And we want to remember chi-squared is kind of like a measurement of how far the data values are away from each other, how far they're spread out. And so that's never a negative number. It's like distance. How far are two things apart? Well, they might be 0 apart. They might be at the same place, but they're never going to be a negative number apart. It's always going to be some positive distance. So the chi-squared distribution values begin with a 0 being the absolute minimum. And you only get a 0 if all the data values are exactly the same. And then if any of the data values are different, then you start to have a positive chi-squared value. And then the more the data is spread out, the larger that gets. But obviously to get very extreme values of very, very far apart is less common than being ones that are just sort of an average distance apart. And you get a distribution as shown here. So that's just something to keep in mind about how this distribution works. And like with the student t distribution that we use for means that we introduced earlier in chapter 7, I guess, you have a slightly different distribution based on your sample size, that there's degrees of freedom. Degrees of freedom is 1 less than the sample size. And that the larger your sample, the more the distribution starts to look like a standard normal curve. And the smaller your distribution, the smaller your sample size, the more your distribution gets skewed to the right, as we can see in this diagram. So properties of the chi-squared distribution, they remind you there's this degrees of freedom, which is the sample size less 1. So subtract 1 from the sample size. And they talk about a table for finding chi-squared values, which we don't care about because we're going to use stack range. So finally, we get to a sample or example problem. So this is going to be example for the p-value method, which is the one we're going to typically focus on and like the most. Do supermodel heights vary less? Listed below are the heights in centimeters for the simple random sample. Remember, that was one of the requirements, a simple random sample. For the simple random sample of female supermodels. Use a 1% significance level, that's our alpha value, to test the claim that the supermodels have heights with a standard deviation that is less than 7.5 centimeters for the population of women. So they're saying that regular non-supermodel women as a total population, they are known to have a standard deviation of 7.5, and they think that to be a supermodel, you're not allowed the wide variety of heights that occur naturally amongst women in general, and that so therefore there's a smaller standard deviation about sort of what heights, how much heights are allowed to vary amongst the group, the subcategory of supermodels. That's the claim. All right, so this will be a hypothesis test. In this case, they're just providing us with the data instead of a summary of the data. So we can talk about how we would do this. Let's see how they move forward. First, they're saying, well, just check the requirements. As I mentioned when I was reading the problem, one of the requirements is met because it's stated that the sample is a simple random sample. So the second requirement was that the population values are normally distributed. And it even said that that's a fairly strict requirement, meaning you really can't get away with overlooking that. So what I mentioned before was that you could look at the sample data and plot it into a histogram and a normal quantile plot and see if it suggests that it's from a normally distributed population. So requirement check 2, they're showing in this case a QQ plot. In checking for normality, we see that the sample has no outliers. The normal quantile plot shows points that are reasonably close to a straight line pattern, and there is no other pattern that is not a straight line. It doesn't systematically deviate from the straight line in some other pattern. So we use that as a basis to say, all right, that means we believe that it is from a normally distributed population. Now, then they immediately jump to putting the data into StatCrunch and getting everything that you need. But they've already set up the null and alternative hypothesis in StatCrunch. So let's go back a couple steps. Maybe I'll just use this slide here to do this. And let's remind ourselves the setup process for a hypothesis test. So here we identify first the claim. We're going to test the claim that the supermodels have heights with a standard deviation that is less than 7.5. So that means we have claim. Sigma is less than 7.5, and these were centimeters. And from the claim alone, we can then construct a null and alternative hypothesis. So from this, the null hypothesis will be where the parameter is set equal to the specified value. So our null hypothesis will be that sigma is equal to 7.5 centimeters. And the alternative hypothesis will be either less than, greater than, or not equal to, based on the claim. If the claim is less than or greater than, then that becomes the alternative hypothesis. So in this case, our claim is the alternative hypothesis that sigma is less than 7.5 centimeters. And we were given an alpha value of 1%. If I just go back to the problem, use a 1% significance level. And then we were given a data set. Okay, so then the basic idea was that when you have the data set, or if you had a summary of the data, then you could go into StatCrunch, use the tool, tell it what the null and alternative hypothesis were and the data set, and then it'll give you a test statistic and a p-value. So then basically, given a data set, then from StatCrunch, we get a test statistic. Now, again, that is a score for the distribution. And so as we've been seeing, this is a chi-squared distribution. So we would get a chi-squared stat test statistic. And we would also get a p-value. The p-value is the probability that if the null hypothesis were true, in this case, if the standard deviation of the population was equal to 7.5%, what would the probability be that our sample would come out the way it did? And so the probability, the p-value probability, is based on the assumption that sigma is equal to 7.5. And then we basically say, if the probability we get, assuming that sigma is 7.5, is very, very low, that means that it's extremely unlikely, if the sigma was 7.5, that our sample would come out like that. And if that is very low, meaning lower than 1% in this case, if the p-value is low, the null must go. Meaning if there's less than a 1% chance that our sample would come out the way it did if sigma is 7 to 7.5, then we reject that sigma is equal to 7.5. We reject the null. And we say, well, this is evidence to support the claim that it's actually less than 7.5, because it's so unlikely that we would get the sample the way we did if it was equal to 7.5 that we think instead that it's less than 7.5. If the p is low, the null must go. We reject the null hypothesis, and we say that the sample is evidence to support the claim that sigma is actually less than 7.5. However, if the p-value is not below the significance level of 1%, if p is not less than alpha, well, then the evidence isn't strong enough to reject the null. We say, well, it's not unlikely enough to get a sample like this if the alternative is wrong. It could very well be that sigma is equal to 7.5, not less than 7.5, because this sample is not that unlikely in that event. And so in that case, we fail to reject the null, and we say that the sample was not sufficient evidence in support of the claim that sigma should be less than 7.5. That's the logic. That's the idea of how we run it. That's how we interpret it. Now, of course, all of that discussion and that logic doesn't stop us from just getting these results from StatCrunch. We just type in the null and alternative hypotheses, and StatCrunch gives us the test statistic and the p-value. So they show that on this slide. They say, okay, so we type that stuff into StatCrunch, and we got a chi-squared statistic, and we got a p-value. Now, as I mentioned to briefly earlier, I want to take note that I was setting everything up in terms of sigma, but in the tool in StatCrunch, they have the null and alternative hypothesis set up in terms of sigma squared, because StatCrunch uses a variance tool, not a standard deviation tool. So what I would need to do in order to put my hypothesis into StatCrunch so that from StatCrunch I can get all this information, I would need to convert the null and alternative hypotheses into sigma squared hypotheses. And I would do that by just squaring the sigma value. So 7.5 squared was 56 point, well, they're having 7.52. They have a little bit more detail than they stated in their problem. So we'll say 56.25. So you had to convert this value into the squared value and then enter those squared values into StatCrunch. And then we get the chi-squared test statistic and the p-value that we need. So that's the idea of the process. Once the conditions are met, we know it's normal, we know it's from a simple random sample, then we can take the sample values and put in a hypothesis test into StatCrunch for the variance by squaring the standard deviation values. And it will give us the test statistic for the chi-square distribution as well as the p-value. So then we can try to, well, here they're showing what I already did. They're showing the setup process here. So they're showing, here was our claim, how it translated. Here was how we set up the null and alternative hypotheses, as I did earlier. Checking that there's a significance level, dump everything into StatCrunch, get those key values. And then we want to be able to draw our conclusion. So in this case, for our p-value was very low. If we look, it was like less than 0.00001. So it says because the p-value is less than the significance level, we reject the null hypothesis. If the p is low, the null must go. The null hypothesis was that sigma is equal to 7.5. And so we reject that and support the alternate that sigma is less than 7.5. And the way that is interpreted or summarized is we say there is sufficient evidence, meaning our sample provides sufficient evidence to support the claim that female supermodels have heights with a standard deviation that is less than 7.5 centimeters for the population of women. It appears that heights of supermodels do vary less than heights of women in the general population. Questions, comments, discussions about this example of performing a hypothesis test for standard deviation?
So yeah, just to clarify, we are agreeing with the statement that we're supporting the alternative claim, right?
Yes, so notice when it says there is sufficient evidence, to support the claim that female supermodels have heights with a standard deviation that is less than 7.5. Note that sigma less than 7.5 was our alternative hypothesis.
Ah, okay, got
So
you.
they're saying there's sufficient evidence to support the claim of the alternative hypothesis. The null that we rejected was that sigma, that's not a sigma, it's a 6. The null hypothesis was that sigma is equal to 7.5. And the alternative hypothesis was that sigma is less than 7.5. So when they say we're supporting less than 7.5, that means we're supporting the alternative hypothesis.
Got it. Yeah.
Okay. Good question. Other questions at all about this? Okay, so now they're going to look at the critical value method, and we've discussed this a little bit in the past. It's not our emphasis because the p-value method is a little bit more straightforward, makes a little bit more sense. The critical value method would be is where you get the critical values you would need, or the critical value you would need to pass with your test statistic in order to hit the alpha level of 1%. So they found out that that's 0.907. Oh no, that's their test statistic. They say the critical value, and here's the graph we looked at before when we were looking at this kind of thing, is there's some place on the distribution, in this case chi-squared, where the area is at the alpha level of 1%. And you find out what that critical value is. So in this case, this is the critical value, meaning that's the distribution score you would need to get to the 1% level. And then you compare your test statistic from your sample and see if your test statistic has a score, in this case, since this is a left-tailed test, below the critical value in the critical region, meaning the region where you're at 1% or less. And if you're in that region, then you reject the null hypothesis. So the slide I think is helpful to remind you, but again, I would recommend whenever allowed to by the problem, and I think most, if not all the problems allow you to use the p-value method, that you use the p-value method. It's a little simpler, but we can refer back to this if we need to determine a critical value. So then they go through how they got those values, and they have a non-technology example here. So let's instead go to see what the problems expect from us in order to apply what we've just looked at. So let's hop over to homework. So here's our homework number 11 on 8.3 and 8.4, and the first half are on 8.3. So I'm going to do something from the second half. There's 39 problems. I think I saw 33 might be a good example to do. And of course, I've done a different problem in the StatCrunch videos on Canvas. So there's another problem there, maybe 28, I think I did, or something like that. All right, but let's take a look at this example. This is number 33 from the homework set. It says, test the given claim. Assume that a simple random sample is selected from a normally distributed population. So that first stuff right up there, assume that a simple random sample is selected from a normally distributed population. Those things that's what allows you to recognize that the requirements have been met. There was 2 requirements, simple random sample, normally distributed population, and they get those out of the way in the first sentence. And that's what I said, most of the time, that's what they're going to do. So when they do that, we don't have to take these data values and do a QQ plot to check for normality or anything like that. There could be a problem where you have to do that. I don't recall seeing which one might be like that, if any. So then it says use either the p-value method or the traditional method of testing hypotheses. We will choose the p-value method. And it says company A uses a new production method to manufacture aircraft altimeters, which I think measures your altitude, how high the airplane is. A simple random sample of new altimeters using this new method resulted in errors listed below. So they're giving us the data set here. Those are the error values, I guess in feet or something. Use a 5% level of significance to test the claim that the new production method has errors with a standard deviation greater than 32.2 feet. So claim for these values is that sigma is greater than 32.2 feet. That's the claim. And as we were just looking at the process, we then use that to create an alternative and null hypothesis. And first part of the problem, we have to pick that. And I'll do that in a second. But that's the claim. I'm just focusing on the claim here. And they say that was the standard deviation of the old method. So they're saying they're trying a new method, and there's a claim that the standard deviation of the new method is greater than the standard deviation of the old method. Then it says, if it appears that the standard deviation is greater, meaning that the evidence supports that claim, does the new production method appear to be better or worse than the old method? Should the company take any action? So those are going to be judgments about what standard deviation is and what this claim means and stuff like that. But let's get through the technical parts of the problem. So in order to conduct this claim, this hypothesis test on this claim, we need the null and alternative hypotheses. So as we've been discussing, the null will be based on the equality statement for the parameter and the specified value. And the alternative hypothesis will be, since our claim is greater than, our alternative will be greater than. If our claim was less than, then the alternative would be less than. If our claim was equality, then the null is our claim and the alternative will simply be not equal to. So that's what we get in this case, which is one of these, I assume, looks like C here maybe. Okay, so now that we've done that, it says find the test statistic. So again, the test statistic is the distribution score that you get from your sample, assuming that the null hypothesis is true. Let's assume the standard deviation is 32.2 feet. How extreme is this sample that we got? And so in order to do that, we would want to put the sample into StatCrunch, tell it what this hypothesis test is, and have it give us the information. So I'm going to open the data in StatCrunch. There it is in a nice little pile. Looks like there's a dozen values here. And so then I'm going to go to Stat And this is a test about standard deviation or variance. And in StatCrunch, they only do variance. So even though we're talking about standard deviation, they both are the chi-square distribution, and we can just convert. And we have one sample. And in this case, with the data is here. So I select the column of the data. And I have to set up my hypothesis test. Now notice it says the hypothesis test for sigma squared for the variance. And our hypothesis was set up in terms of sigma. So I need to square both of these values for here. So I'm just grab my little calculator, take 32.2 and square it. And I get that number. And so I'm going to put that my null hypothesis is that the variance is that number, because that's the same as the standard deviation being 32.2. Then my alternative is that we have a larger value, so I'm going to change the variance to being greater than that number. And that's it. So with those things entered in, I will hit compute. And I get my little box of results, similar to what they showed in the slides. So at this point, they are asking for the chi-square distribution. And notice it says here chi-squared stat. And they want that to 2 decimals. So I'm going to have to copy that over and round the 4 up to a 5, since it was followed by a 7. And now they want us to determine the critical values. So here, even though they said we could use the p-value approach, they're still forcing us to determine the critical values, which would be using the critical value method. So they're kind of trying to make sure that you could use either, even though I think the p-value is better. So let me just show you the idea of how we do that. So in order to get the critical value, we need to look at the chi-square distribution and see where on that distribution you would need to be for the alpha level of 5% to be the critical area, to be the critical region. So again, sometimes you want to draw a little picture of this. So here's my chi-square distribution. And I'm going to try to remind myself that it's lopsided by stretching it out a little bit more to the right. And this is a test as to whether sigma is greater than a certain value. So that means this is a right-tailed test. And so somewhere over here on the right is going to be a place where the area there is 5%. Somewhere over there, that's the case. And the score value, the chi-squared value, where that happens is the critical value, because we could then compare our test statistic to that critical value. And if 35 is larger and to the right of where the 5% place is, well, then that's big enough so that this has a p-value less. And we can see it's going to be because the p-value is like less than 1%. But nonetheless, they want the critical value. So how do I get that? This tool doesn't tell us the critical value. We never told this tool what the alpha value of 5% is. It just told us how extreme our sample was. So to find out where 5% is on the chi-square distribution, I have to use another tool. So I'm going to go to stat. I have to use the chi-squared calculator. So I'm going to go calculators. And there it is, chi-squared. So under calculators, you have chi-squared. And then you get the calculator with the little picture that I was just alluding to over there. And we want the place on this distribution where the area to the right is 5%. So I'm going to put that the area goes to the right instead of the left. I'm going to put that it's 5%, but I also need to put in the correct degrees of freedom. There were 12 data values, so it'd be 11. You could also see in the box here that it tells you DF, the degrees of freedom is 11. So I need to change this 10 to an 11. So when I put in the degrees of freedom of 11, it knows which exact distribution to use. I want the area to the right to be 5%, and I compute, and it shows me where that happens, and that happens at this chi-squared score. So that is my critical value, and they want that to 2 decimal places. So it's going to be 19.68. So I'm going to put that in, round that up to an 8, and got me some credit. So that's a little tricky because we haven't done, I'm emphasizing the p-value. I think the p-value is a much friendlier way and easier way to understand what you're doing while you do it. But then they want us to draw a conclusion based on the critical value. So as I was pointing out, once you get to the critical value of 19.68, any distribution scores higher than that have less than a 5% chance of occurring, meaning they have a p-value of less than 5%. And that's where you need to be past our significance level. And so in this case, we can even see our p-value is way less than that, but that score 35 is way past 19. So since the test statistic is greater than the critical value in this case, we reject the null hypothesis and conclude there is sufficient evidence to support the claim that the new production method has errors with a standard deviation greater, the alternative hypothesis, greater than 32.2 feet. How do you guys feel about that?
You recorded a video on this, right? That we can go back and like.
Well, you can watch this video if you want to scale to the end because we're still
Oh,
recording.
gotcha.
And I'll post all of this. I believe the one I did in the StatCrunch videos is number 28. And I'm not sure from my memory how that differs from this. It's certainly going to use the chi-squared tool and do a variance test to do a hypothesis test. I don't remember whether that one had the critical value or the p-value or what.
Okay. I forgot this one was recorded. So yeah, that works great.
Yeah,
Thank
you
you.
can just skip over the slides that, you know, if you remember that part and just get to this example at the end if you need to.
Thank you.
Now let's see, we got a couple minutes left here. Let's see if we can draw their final conclusions here. All right, so it says the variance appears to be something compared to the past. So the variance seems to be more, so greater than, we can choose that. So the new method appears to be better, worse, or similar. What do we think? Is it better, worse, or similar for the errors from the new altimeters to have a wider variation? What do you guys think?
I think it would be similar, but I had a question.
Okay, fire away.
So what does DF represent again?
So degrees of freedom is a phrase that basically talks about how well your sample is sampling the population, which basically means bigger is better. So it's a label for a number that's one less than the sample size in this case. And we're going to do problems, I think, in chapter 11, where it gets a little bit more complicated. But for now, so far, whenever we've had degrees of freedom, which has been a t distribution and a chi-square distribution, degrees of freedom is always just one less than the sample size. So in this case, our sample had 12 items in it. So our degrees of freedom was 11. And notice that it put that in StatCrunch. So once we gave let me close our calculator here. Once we gave the sample to StatCrunch, it told us here in its summary that the degrees of freedom was 11.
Okay, I didn't realize that. Okay, cool.
Okay, so I think they're going to, I'm just trying to tell you what I think, and I don't remember this problem, so we'll find out. Maybe I'm wrong. This is a device measuring your altitude when you're flying a plane. And I think what's important about that is accuracy. And you have a higher level of accuracy if when there are errors, they don't deviate too far from the real value. If you're really at 1,000 feet and your altimeter is telling you, yeah, you're like 990 feet. Well, you're only 10 feet away. It's not a big deal. But if you're at 1,000 feet and it's telling you you're at 800 feet, well, that's not good. The larger the error size deviating from each other and the real value, the worse that device is for measuring what it's supposed to measure. So I think we're going to want to say that since the variation in the readings from these new altimeters is greater than it was in the past, this appears to be worse because there will be more altimeters that have errors. Therefore, the company should take immediate action to reduce the variation. All right, let's just go with that, see what they say. They like that. So that's a little bit of a common sense, but they're walking us through that because they want us to realize that there are reasons people want to test standard deviation. If you have a device that measures something, what's most important is accuracy. And lack of accuracy creates a deviation in your answers, and that can be measured with a sample, in which they took all the answers and looked at all the errors and looked at how far apart they were. Now, this isn't technically all you'd want to know, but I think that's what they're looking for, so that's why I wanted to show that to you. And we are almost out of time. So any questions before we finish up here for today?
So I just wanted to clarify that the test statistic was the chi-square stat, right?
Exactly. The
Okay.
chi-squared stat, the test statistic is the statistic you get from your sample. The critical value has nothing to do with your sample. It only has to do with the alpha value. So when I got the critical value from the calculator, which I think I could show here, notice nowhere in here is our sample values, nowhere in here is our test statistic, just 5% and how many are going to be in our sample, or the degrees of freedom, one less than how many in our sample. And so they tell you the score that you need to hit the 5% level, that's the critical value.